A small uranium fuel pellet, whose size is only about that of a peanut, contains an astonishing amount of energy inside it, enough to generate nearly 1 million kilowatt hours of electricity. This is sufficient to keep thousands of homes powered for an entire year. But the question is, how is enriched uranium actually produced? How can such a tiny object store such immense power? Today, we are setting out on a journey to uncover this mystery, where we will explore one of the world's largest high-grade uranium deposits and a nuclear fuel factory, and see how this dangerous element is transformed from deep within the Earth into clean energy. This is a journey that is not only astonishing, but also has the power to completely change the way you think, especially about this tiny pellet that is silently powering your world. The story of enriched uranium is deeply connected to the history of modern science. In 1789, the German chemist Martin Heinrich Klaproth first identified uranium as a chemical element, at a time when no one had any idea of the enormous energy hidden inside it. This discovery marked the beginning of a journey that would eventually reshape the direction of global energy in the future. In 1896, a surprising discovery was made when the French scientist Henri Becquerel observed that uranium emits radiation on its own without any external influence. This phenomenon was later named radioactivity. This discovery laid the foundation for a new era of research, inspiring Marie Curie and Pierre Curie to discover other radioactive elements, such as radium and polonium. Then, in 1932, James Chadwick discovered the neutron, a subatomic particle that later became the key to nuclear fission. Just a few years later, in 1938, Otto Hahn and Fritz Strassmann demonstrated that the rare isotope uranium-235 found in natural uranium splits when struck by a neutron. And during this process, an enormous amount of energy is released. Natural uranium is composed in such a way that about 99.3% of it is uranium-238, which does not easily undergo fission, while only 0.7% is uranium-235, the active isotope capable of sustaining a chain reaction. Increasing this small fraction is called enrichment. During World War II, the United States took a historic step in this field, bringing together the world's top scientists under a secret program known as the Manhattan Project. This project was led by renowned scientists such as Enrico Fermi and Robert Oppenheimer. They developed advanced techniques like gaseous diffusion and high-speed centrifuges, which are capable of separating isotopes based on the slight difference in their mass. The most dramatic outcome of this research came in August 1945, when the atomic bomb called Little Boy was dropped on Hiroshima, using highly enriched uranium-235. After the war, the world decided to use this power for construction instead of destruction. Nuclear technology was redirected toward peaceful purposes, especially electricity generation. For use in power plants, uranium only needs to be enriched to about 3 to 5%, while weapons-grade uranium requires enrichment of over 90%. And this difference remains a major global concern regarding nuclear proliferation even today. In the modern era, enriched uranium powers reactors that generate about 10% of the world's electricity. And the entire story begins deep within the Earth. Uranium production in the world depends on a few specific countries, with Australia, Kazakhstan, and Canada being the most prominent. They together account for more than 60% of global production. Uranium is usually found in a mineral form called uraninite, and its concentration typically ranges between 0.1 and 2%. However, one region in Saskatchewan, Canada, is completely unique in this regard, home to the richest uranium deposits in the world. Here, the ore can contain more than 20% uranium, which is almost 100 times higher than the global average. However, accessing this valuable resource is not easy, because it is covered by a thick layer of sandstone that is completely saturated with underground water. To deal with this challenge, engineers use a special technique called artificial ground freezing. In this process, special drill bits are used whose tips are made of tungsten carbide, allowing them to bore through hard rock and install a complete network of cooling pipes. Inside these pipes, a brine solution containing calcium chloride is circulated, which has cooled down to -22 degrees Fahrenheit. This extremely cold liquid freezes the water present in the pores of the sandstone, forming a strong, impermeable wall of ice that safely isolates the uranium deposit. Installing each pipe takes about 8 days, and the entire system requires approximately 200 such pipes. After that, the extraction process begins with a small pilot hole, which guides the larger drilling equipment in the correct direction. Then a reamer drill enlarges the hole, breaks the rock, and drops the fragments into collection chambers below. The entire process is carried out via remote control to ensure workers are protected from risks such as ground collapse and radiation. Inside the mine, fresh air circulation is maintained every 20 minutes to keep the environment safe. When the raw material reaches the surface, it is passed through a radioactivity scanner that verifies the uranium content, typically between 15% and 18%, which is considered exceptionally high quality. After that, the material is crushed into fine sand-like particles, mixed with water to form a slurry, and then pumped to the surface. Finally, specialized trucks transport this mixture about 50 miles to a processing mill, where the next stage begins. After reaching the processing mill, the slurry is treated with acid, where through a careful chemical process, uranium is dissolved while the remaining minerals settle at the bottom of the tank. Next, the uranium-rich solution is separated and passed through various chemical stages to further purify it, and then it is heated to approximately 1,560 degrees Fahrenheit. At this stage, uranium is converted into uranium hexafluoride gas, which is then fed into high-speed centrifuge machines. Inside these machines, due to the slight weight difference between isotopes, uranium-235, which is slightly lighter, begins to collect toward the center of the rotor. Finally, the result of this entire process is a thick, dark-colored powder, which is packed into securely sealed 55-gallon steel drums, marked clearly with radioactive warning labels. These drums are then transported to a nuclear fuel manufacturing facility, where uranium undergoes further chemical transformation stages. Moving through different oxide forms, it eventually becomes uranium dioxide powder, which has exactly the right properties for fuel production. This powder is compressed under several tons of hydraulic pressure and shaped into small cylindrical pellets about the size of a peanut. What is astonishing is that a single pellet contains as much energy as approximately 1,800 pounds of coal, or 150 gallons of oil. After that, the pellets are placed in industrial furnaces and sintered at extremely high temperatures for 24 hours. This process removes internal voids, significantly increasing both their density and strength. After leaving the furnace, advanced robotic arms precisely arrange about 30 pellets into a special metal tube. This tube is made of zirconium, a metal that not only withstands extreme heat and corrosion, but also allows neutrons to pass through easily, which is essential for the fission process. Next, both ends of the tube are sealed using automatic welding, creating a complete fuel rod. 37 such fuel rods are then assembled in an organized pattern to form a fuel assembly, which is carefully weighed with high precision to verify the amount of uranium it contains. Interestingly, before being inserted into the reactor, these assemblies emit such low radiation that workers can safely handle them while wearing protective clothing. Once they reach the power plant, the fuel assemblies are installed in the reactor core, where a total of 5,760 rods operate across 480 channels. This is where the real power begins. When neutrons strike uranium-235 atoms, they split apart, releasing energy and more neutrons. These newly released neutrons then strike other atoms, triggering a self-sustaining chain reaction. This continuous process generates enormous heat, which is controlled by advanced automatic safety systems. The entire reactor is enclosed within thick concrete walls nearly 6 feet thick and is designed to shut down automatically if temperature or pressure rises to dangerous levels. The heat produced converts water into steam, which spins massive turbines. These turbines are installed in vast halls, approximately 1,300 feet long and as tall as a 20-story building. Spinning at about 100 rotations per minute, each turbine drives a generator capable of producing over 750 megawatts of electricity, enough to power around 500,000 people. After about 1 year of use, these fuel assemblies lose their efficiency, but their journey does not end here. After use, these fuel rods become so hot and highly radioactive that they must be immediately transferred to special cooling pools. These pools are about 26 feet deep, where the rods are kept underwater for at least 10 years to reduce their heat and radiation to safe levels. At present, more than 700,000 spent fuel rods are stored at various facilities around the world at the bottom of these pools. This is the silent yet powerful system that continues to provide energy to our world, a journey that begins deep within the earth and ends at the heart of modern technology. Thank you for joining me on Metrixor. I'll see you again in the next video.